Hi, and welcome to day 24 of Just Start Programming, the Rust programming language. For those of you who happen to view my video, you might have noticed that I'm taking a slow and gradual approach in learning Rust. This approach is intentional, and it is because I'm a slow learner. If you're like me, please stick around, as this is not a tutorial lesson and the content is long and I don't want to take any shortcuts. So there are so many approach in learning a programming language, but if you're serious in learning Rust, you could also consider my approach. And so join me once again, do it live in one take, no shortcuts, no secrets, and let's just start programming. Okay, so the other day I think we were this one. No, not this one. Yeah, we were trying out running code on cleanup with the drop trait. So let's just quickly glance through to refresh our memory. So we have this drop trait. And the drop trait requires you to implement one method named drop that takes a mutable reference to self. To see Rust calls drop, let's implement drop with print line. Okay, so I think we tried this the other day. You have customer smart pointer struct with data as string, and then here it implements the drop trait. So it says here it will be this function drop, which takes in a mutable reference to itself. So this one will just print out the data, customer pointer with data, so data, so whatever string that you have here. And here you have the main. So you have custom start pointer my stuff and custom start pointer other stuff. And when this one is after this line, it will print out other stuff and then my stuff. Yeah, other stuff and my stuff. Okay, here Rust automatically called drop. So the variables are dropped in reverse order of their creation. So D was dropped before C. So this is D, it was dropped before C. And we was checking if the order was correct. So we tried to move things around the other day. Let's see the code. Yeah, so here we have D and C. And here C was dropped. Yeah, so the drop function can be called explicitly also. So that means if we do this, then C will be called first, and then D, other stuff. We can run this one. Yeah, so my stuff is called first, mainly because of this function here, and then other stuff next. Okay. Yeah, so the drop trait, implementing drop. This is if you want to handle your own drop implementation. So it's like garbage collecting also. Okay, let's come back to this. What else is there? Here, dropsy is called. So when dropsy is called here, it will output dropping custom smart pointer with data, some data. So created and then some data, and then this one. But if we don't have this, this will be printed first. Okay, then let's move on to reference counted smart pointer. RC with the type T, the reference counted smart pointer. In the majority of cases, ownership is clear. You know exactly which variable owns a given value. However, there are cases when a single value might have multiple owners. For example, in graph data structures, multiple edges might point to the same node, and that node is conceptually owned by all of the edges that point to it. A node shouldn't be cleaned up unless it doesn't have any edges pointing to it, and so has no owners. You have to enable multiple ownership explicitly by using Rust type RCT, which is an abbreviation for reference counting. So RC is reference counting. So it keeps track of the number of references to a value to determine whether or not the value is still in use. If there are 0 references to a value, the value can be cleaned up without any references becoming invalid. Imagine a reference counter as a TV in a family room. When one person enters to watch TV, they turn it on. Others can come into the room and watch TV. When the last person leaves the room, they turn off the TV because it's no longer being used. Ah, nice. It's a good analogy. If someone turns off the TV while others are still watching it, there would be an uproar from the remaining TV watchers. We use reference counter type when we want to allocate some data on the heap for multiple parts of our program to read, and we can determine at compile time which part will finish using the data last. If we knew which part would finish last, we could just make that part the data's owner. And the normal ownership rules enforced at compile time would take effect. Note that reference counter is only for use in single-threaded scenarios. Okay, so this is important to note, to remember. When we discuss concurrency in chapter 16, which is the next chapter, we'll cover how to do reference counting in multi-threaded programs. So yeah, so I assume it's not this one, something else. Using reference counter to share data. Let's return to our cons list example in 15-5. Recall that we defined it using box T. So box T is a smart pointer. This time we'll create two lists that both share ownership of a third list. Conceptually, this looks similar to this one. There are two lists, B and C, sharing ownership of a third list A. Okay, B is a list, C is a list, and then A is also sharing with them this list. We'll create list A that contains 5, then 10. Then we'll make two more lists. B starts with 3 and C. 3 and C that starts with 4. Okay, C starts with 4, B starts with 3, A starts with 5. Both B and C lists will then continue on to the first A list containing 5 and 10. 5 and 10. In other words, both lists will share the first list containing 5 and 10. Okay. Trying to implement this scenario using our definition of list with box T won't work as shown in 15-17. Okay, so we have an enum of const I32 box list. So here create a list const and nil A const 5 and box const 10 box new nil. Okay, so this one is this part. Then this one 3 box new A, 3 box new A. Okay, that part. And of course this one is 4 box new A. So it says here it will not compile. Why? We are not allowed to have two lists using box T. We try to share ownership of a third list. When we compile this code, we get this error. Use of moved value A. Okay, so A move occurs because A has type list, which does not implement the copy trait. There's list. Yeah. B equals const 3 box new A. Okay, so here A, yeah, value moved here. Value used here after move. Okay. Because at this point, the value of A was moved here. So B takes ownership. But then here, you cannot use it here. Of course, it will complain. The const variants variants own the data they hold. So when we create the B list, A is moved into B. A is moved into B. And B owns A. Then when we try to use A again, when creating C, we're not allowed to because A has been moved. Yeah. We could change the definition of const to hold references instead. Then we would have to specify lifetime parameters. By specifying lifetime parameters, we would be specifying that every element in the list will live at least as long as the entire list. This is the case for the elements and lists in listing 15-17. 15-17. Yeah, okay. Here. But not in every scenario. Instead, we'll change our definition of list to use reference counter T in place of box T. Okay, so in this case, instead of box T, we use RC, reference counter. What's the reason for that? Let's see. Each const variant will now hold a value and a reference counter pointing to a list. So it's a reference counter pointing to a list. Box T is also pointing to a list. Box is pointing to this. Okay, let's continue. When we create B, instead of taking ownership of A, we'll clone the RC list. So where's the clone? Here. So does it mean that the reference counter is implementing clone? Let's see. We'll clone the RC list that A is holding, thereby increasing the number of references from 1 to 2 and letting A and B share ownership of the data in that R reference counter list. So we are cloning the reference counter. Okay, so ampersand A, ampersand A, ampersand A. Okay, so it's like we're borrowing. Where was it? Okay, every time we call RC clone, the reference count to the data within the reference counter will increase and the data won't be cleaned up unless there are 0 references to it. Unless there are 0 references to it, does it mean that this one look like this B? Okay. We need to add a use statement to bring reference counter into scope because it's not in the prelude. Yeah, so we are seeing this term again. Preludes. A prelude is a collection of names that are automatically brought into scope of every module in a crate. So it's not automatically added. So that's why we use use statement here. RC. We create the list holding 5 and 10 and store it in a new RC list. Here, new. So in this case, we are using new, not clone, but new. Const 5, then RC new again, const 10. How was it for box last time? I already forgot. Let's see. Box. My box. Oh, there's also new here for my box. Yeah, so this is custom box, my box. It implemented new. Okay. B. Okay, here. Then when we create B and C, we call the RC clone A function and pass a reference to the RC list in A as an argument. We could have called A.clone rather than RC clone. What was A? A.clone. Yeah. We could have called A.clone rather than RC clone, but Rust's convention is to use RC clone in this case. The implementation of RC clone doesn't make a deep copy of all the data like most types implementation of clone do. So it's not a deep copy. The call to RC clone only increments the reference count. Okay, so it only increments reference count, which doesn't take much time. Deep copies of data can take a lot of time. By using RC clone for reference counting, we can visually distinguish between the deep copy kinds of clones and the kinds of clones that increase the reference count. Okay, so RC clone, just take note, it's only increases the reference count. It doesn't do a deep copy. When looking for performance problems in code, we only need to consider the deep copy clones and can disregard false to RC clone. Okay. So try to avoid deep copy clones if we want it to be performant. Cloning an RC reference counter increases the reference count. Let's change our working example in listing 15-18 so we can see the reference counts changing as we create and drop references to RC list in A. Okay. 15-19 will change main so it has an inner scope around C. Inner scope around C, so it's this part, inner scope around C. Then we can see how reference count changes when C goes out of scope. Print line count after creating C. Oh, this is strong count. There's another function here, strong count. A, B, okay, so it's the same as the previous one. The only difference is we added these things, and then C is inside this scope. Count after C goes out of scope. Okay. At each point in the program where the reference count changes, we print the reference count, which we get by calling the RC strong count function. This function is named strong count rather than count because reference count type has a weak count. Oh, there's another one, weak count. Strong count and weak count. We'll see what weak count is used in preventing reference cycles using weak. Is it in the advanced chapter, most likely. This code prints the following: cargo run. Okay, let's see, we can trace from here. Count after creating A plus 1. Count after creating A, okay. Then count after creating B equals 2. Count after creating B equals 2. Because of the clone, okay. Count after creating C equals 3. Yeah, here, because of the clone also. And then count after C goes out of scope equals 2. Equals 2. Okay, so it's because C is already out of scope after this. Then we are printing 2. Okay. I think that's the analysis. Okay, we can't see in this example is that when B and A go out of scope at the end of main, the count is then 0. And then RC is reference count is cleaned up completely using RCT. Allows single value to have multiple owners. And the count ensures that the value remains valid as long as any of the owners still exist. Okay, so this is the feature of this reference count. Allows a single value to have multiple owners. And the count ensures that the value remains valid as long as any of the owners still exist. Via Immutable references allows you to share data between multiple parts of your program for reading only. Immutable references. If reference count allowed you to have multiple mutable references too, you might violate one of the borrowing rules discussed in Chapter 4, which is multiple mutable borrows to the same place can cause data races and inconsistencies. Cause data races and inconsistencies. I'm not sure if it's talking about concurrency, but oh, concurrency is here. So soon we'll be learning this part. Okay. But being able to mutate data is very useful. The next section will discuss interior mutability pattern and the ref cell type that you can use in conjunction with reference counter, reference counting to work with this immutability restriction. Okay, so before we move on, I wanted to check and verify something here. Let's try this one. Let's see. Okay, we don't have box. This is my box. Custom smart pointer. Oh, const. Okay, so we can just append it here. Or do I have another Visual Studio Code? Oh, this is the only. So what was that? Enum. What list was that? List. So here we have cons, then nil. Okay, but before that we do a use std rc, then rc. Okay, and here we have I32, then rc list. So list this one. Then use create list const nil. We have it there. Use, okay, we don't have it. Okay, and then in main, let me comment about this one. Example is already done. Then let me see. I think there was some kind of a equals to what was that? RC new. Okay, then we have 5. RC new value 10 and RC new, right? Oh, error. Oh, forgot about cons. Okay, so this should be cons. Then we'll just add over here, and then here, repeat, ready for this. Also here, cons, and somehow I'll just close this part. Okay. Then let B plus RC clone. Oops. Let B equals RC clone which one? Let A percent A. But we need to put in how was that? Cons. So 3, and here need to close this, then this one C, and what's it? What's the number? 4. RC clone A. Okay. And then we do a print. Let me just copy this. I could have copied it earlier, but I wanted to type. So typing can help you retain information also. And here we close this one, then the one, copy this. We already know what is the output. Let me just put this in and we move things around and see what will happen. Okay, so let's run this. 1, 2, 3. Count after C goes out of scope. 1 equals to 2. Yeah. So after this, there's no way for us to display from 2 to 1 and then finally 0. So it ends here. Okay, let's do something about that. If we put this within this code like that, I don't know if that's possible. Then then we can C will be out of scope here, so B after B is after B. Okay, so C will be out of scope here, and B will be B will be out of scope here actually. Count after creating A, yes, that is count after creating A. And here count after creating B, count after creating C. So count after let me change this. After C is out of scope. Okay, B is here, so here B is out of scope at 989. After B is out of scope. Count after C. Oh, okay, so we don't need this. Let's see. There. You can see count after C is out of scope. C is out of scope here, so now we have 2. And then after B, count after B is out of scope, so you have 1. Okay. Let's do another one. So maybe let's enclose this in curly brackets. Then let's do another print here. Count after A is out of scope. So that at least we will see the count. Oops. Not found in the scope. Oh, yeah, it's not found in the scope. What can we do? Let's not do it like that. I'm sure there's another way. So on this one, if we do a drop A, this one will complain because RC strong count A, drop A. Can we? No, we cannot do a borrow as well. What will happen? That's interesting. What will happen? Drop. I think it won't be drop. Let's see. Yeah, it won't be drop. Still have 1. We cannot make it 0. Cannot print out a 0. Because A will be A will only be out of scope after line 91. Okay, anyway, we have seen the counter reference count. Yeah, we have a reference count. Let's move on to the next topic. Okay, ref cell and the interior mutability pattern. So interior mutability is a design pattern in Rust that allows you to mutate data even when there are immutable references to the data. Allows you to mutate data even when there are immutable references to the data. Normally, this action is disallowed by the borrowing rules. To mutate data, the pattern uses unsafe code inside the data structure to bend Rust's usual rules that govern mutation and borrowing. Oh, it's unsafe. For sure, there's a use case for this. Unsafe code indicates to the compiler that we're checking the rules manually instead of relying on the compiler to check them for us. Does it mean that it will reduce the compile time also? We will discuss unsafe code more in chapter 20. Chapter 20, Advanced Unsafe Rust. Okay. We can use types that use the interior mutability pattern only when we can ensure that the borrowing rules will be followed at runtime, even though the compiler can't guarantee that. The unsafe code involved is then wrapped in a safe API, and the outer type is still immutable. Let's explore this concept by looking at the reference cell type that follows the interior mutability pattern. Enforcing borrowing rules at runtime with ref cell. Unlike, okay, let's just call this RC. RC, the ref cell type represents single ownership. This one represents single ownership, while this one can have multiple ownership. This one is single over the data it holds. So what makes ref cell different from a type like boxt? Recall the borrowing rules you learned in chapter 4. At any given time, you can have either one mutable reference or any number of mutable references, but not both. So you cannot mix mutable and immutable. References must always be valid. Okay, with references and boxt, the borrowing rules invariants are enforced at compile time. Okay, yeah, we've learned that in the previous one, smart pointer. The borrowing rules invariants are enforced at compile time. With ref cell, these invariants are enforced at runtime. Okay, boxt, borrowing rules invariants enforced at compile time. Ref cell invariants are enforced at runtime. Okay, so it's at runtime. With references, if you break these rules, you get a compiler error. With ref cell, if you break these rules, your program will panic and exit. Okay. With references, if you break these rules, you get a compiler error. Yeah, this one you already know. With the ref cell, if you break these rules, the program will panic and exit. Okay. Is there a way to handle this one? Graceful exit using error handling techniques. The advantages of checking the borrowing rules at compile time are the errors are that errors will be caught sooner in the development process, and there is no impact on runtime performance. Yeah. So that there's no impact on runtime performance because all the analysis is completed beforehand. For those reasons, checking the borrowing rules at compile time is the best choice in majority of cases, which is why this is Rust's default. So we are now in advanced territory. The advantage of checking the borrowing rules at runtime instead is that certain memory save scenarios are then allowed. Okay, certain memory save scenarios are then allowed, where they would have been disallowed by compile time checks. Static analysis like the Rust compiler is inherently conservative, which is good. Some properties of code are impossible to detect by analyzing the code. The most famous example is the halting problem, which is beyond the scope of this book, but an interesting topic to search. Halting problem. This halting problem. Interesting topic to search. Let's see. Fundamental concept in computer science that asks whether it's possible to determine for any given programming input whether that program will eventually halt or run forever in an infinite loop. I don't want to confuse myself. Maybe we can look it up in some other time. Alright. Because some analysis is impossible, if the Rust compiler can't be sure the code compiles with the ownership rules, it might reject a correct program. Okay, some analysis is impossible. So although it's correct, it might reject the correct program. In this way, it's conservative. If Rust accepted an incorrect program, users wouldn't be able to trust in the guarantees Rust makes. However, if Rust rejects a correct program, the programmer will be inconvenienced, but nothing catastrophic can occur. The ref cell type is useful when you're sure your code follows the borrowing rules, but the compiler is unable to understand and guarantee that. Similar to RC, ref cell is only for use in single-threaded scenarios and will give you a compile time error if you try using it in a multi-threaded context. We'll talk about how to get the functionality of ref cell in a multi-threaded program in chapter 16. Here's a recap of the reasons to choose boxd, RC, and ref cell. Okay, this is good. Reference counter enables multiple owners of the same data. boxd and ref cell have single owners. Okay. boxd allows immutable or mutable borrows checked at compile time. RC allows only immutable borrows checked at compile time. Immutable or mutable borrows at compile time. Immutable borrows checked at compile time. Ref cell allows immutable or Mutable borrows checked at runtime. Okay, so it's the best of both worlds, immutable or mutable. So ref cell. RC is reference counter only allows immutable borrows checked at compile time. Only immutable. Well, this one allows immutable or mutable. Yeah. At compile time. This is compile time. This is immutable or mutable at runtime. Okay. Because ref cell allows mutable borrows checked at runtime, you can mutate the value inside ref cell even when the ref cell is immutable. Ref cell is both immutable and mutable at runtime. So it's during runtime. You can mutate the value inside ref cell even when ref cell is immutable. Okay. Mutating the value inside an immutable value is an interior. Okay, mutating the value inside an immutable value is the interior mutability pattern. Let's look at a situation in which interior mutability is useful and examine how it's possible. Useful. Okay, let's see. Interior mutability, a mutable borrow to an immutable value. A consequence of the borrowing rules is that when you have an immutable value, you can't borrow it mutably. Yeah. For example, this code won't compile. Yeah, so X is immutable, but we want to borrow it as mutable. Why? If you try to compile this code, you get the following error. Cannot borrow as mutable. Okay. Consider changing this to mutable. Oh, that's the other suggestion. However, there are situations in which it would be useful for a value to mutate itself in its methods but appear immutable to other code. Code outside the value's methods would not be able to mutate the value. So that's why it's called interior mutability pattern. Using ref cell is one way to get the ability to have interior mutability. But ref cell doesn't get around the borrowing rules completely. The borrow checker in the compiler allows this interior mutability, and the borrowing rules are checked at runtime instead. Okay, so it's like it's keeping it, and only the borrowing rules are checked at runtime. If you violate the rules, you get a panic instead of a compiler error. Panic because it's runtime, it's running. Let's work through a practical example where we can use ref cell to mutate an immutable value and see why that is useful. Okay, let's take a look. A use case for interior mutability, mock objects. Okay, so this is one use case. Sometimes during testing, a programmer will use a type in place of another in order to observe particular behavior and assert that it's implemented correctly. Yeah, so those are mock data or mock objects. During testing, this placeholder type is called mock dummy data during testing placeholder. This placeholder type is called a test double. Test double. Okay. It sounded like a stunt double. Yeah. Think of it in the sense. Okay. So it's here. Stunt double in filmmaking, where a person steps in and substitutes for an actor to do a particularly tricky scene. The test double stand in for other types when we're running tests. Mock objects are specific types of test doubles that record what happens during a test, so you can assert that the correct actions took place. Okay. Rust doesn't have objects in the same sense as other languages have objects, and Rust doesn't have mock object functionality built into standard library as some other languages do. However, you can definitely create a struct that will serve the same purpose as a mock object. Oh. So in order for you to create a mock object, you need to learn advanced Rust. Here's the scenario we'll test. We'll create a library that tracks a value against a maximum value and sends messages based on how close to the maximum value the current value is. This library could be used to keep track of a user's quota for the number of API calls they're allowed to make, for example. Okay, so this is one useful use case. Keep track of users' quota for a number of API calls they're allowed to make. Okay. Our library will only provide the functionality of tracking how close to the maximum value is and what the message should be at what time. Applications that use our library will be expected to provide the mechanism for sending the messages. The application could put a message in the application, send an email, send a text message, or do something else. The library doesn't need to know the detail. All it needs is something that implements a trait to provide called messenger. Okay. Trait called messenger. Okay. Pub trait messenger. So it has a method send self and then the message. And you have a struct called limit tracker. Okay, so this one is, if you see the apostrophe, that's lifetime. T messenger. Okay, messenger. Oh, what is this? Reference to a lifetime. T value, use size, max use size. So these are numbers. Then here, okay, we are implementing functions for limit tracker. So this lifetime where T is messenger. Where T is messenger. Okay. Function new messenger. Okay, max use size. It returns limit tracker having exactly the same lifetime. Limit tracker messenger value 0 max. Then here you have set value. Self value equals value. Past here you have this value here. Let percentage of max equals self that value as floating point divided by self max as f. Okay, so I think this is what should we call this one? Forgot the term, but it's making self max as floating point 64. Because here it's use size, we don't know what exactly is the size. If percentage of max is greater than equal to 1, as we have max. Okay, percentage of max is only in this function. Self messenger send error, you are over your quota. Here, urgent warning. Here, You've used up 75% of your quota. Okay. Okay, I think the explanation would be here, although I tried my best to interpret it, but I might be wrong. Let's see. One important part of this code is that the messenger trait has one method called send. Send. That takes an immutable reference to self and the text of the message. Okay. Self, okay, so it's immutable, cannot change in the message. This trait is the interface our mock object needs to implement so that the mock can be used in the same way as real object is. The other important part is that we want to test the behavior of setValue method on the limit tracker. We can change what we pass in for the value parameter, but setValue doesn't return anything for us to make assertions on. Let's refer to this one. Okay, setValue method on the limit tracker. SetValue method on the limit tracker. Okay. We have value. Okay, value is self is mutable. But value is not. We can change what we pass in for value parameter, but setValue doesn't return anything for us to make assertions on. Okay, setValue doesn't return. Yeah, so it doesn't return anything. We want to be able to say that if we create a limit tracker with something that implements messenger trait and a particular value for max, when we pass different numbers for value, the messenger is told to send the appropriate message. Okay. So this is where the mock, mock object. Instead of sending an email or text message when we call send, we'll only keep track of the messages it's told to send. We can create a new instance of the mock object called limit tracker that uses the mock object, call setValue method on limit tracker, and then check that the mock object has messages we expect. Okay, here it shows an attempt to implement a mock object to do just that, but MorrowChecker won't allow it. Okay, so now we are venturing into testing. Test-driven development. Okay. We are creating struct mock messenger, sent messages, flex string, mock messenger, new, and implement messenger for mock messenger, send, implement messenger. Okay, the trait messenger. So it should implement send, self message, send messages that push. Oh, why do we have send messages that push? Because it's a vector. String from message from here. And in the test, it sends an over 75% warning message. Mock messenger, okay, mock messenger new, mutable limit tracker equals limit tracker new at mock messenger. So borrowing 100. Limit tracker set value 80. What happened here? Limit tracker new. So limit tracker new. It will return limit tracker the mock messenger. Why do we need mock messenger? Messenger. Mock messenger new 100. Okay. And this test code defines a mock messenger struct. Mock messenger struct that has sent messages filled with a backup string. Let's look for something significant here. We then implement messenger trait for mock messenger. Messenger trait or mock messenger. Messenger. Okay, send. Where were we? So we can give a mock messenger to a limit tracker. Oh, okay. So we just implemented messenger so that we can pass it into limit tracker. In the definition of send method, we take the message passed in as parameter and store it in the mock messenger list of sent messages. Okay, so that's the purpose of the vector, it seems. Sent messages. In the test, we're testing what happens when the limit tracker is told to set value to something that is more than 75% of the max value. First, we create a new mock messenger, which will start with an empty list of messages. Then we create a new limit tracker and give it a reference to the new mock messenger and a max value of 100. Yeah, so that's that part here. We call the set value method on the limit tracker with a value of 80. Okay, so value of 80, which is more than 75% of 100. Then we assert that the list of messages that the mock messenger is keeping track of should now have one message in it. However, there's one problem with this test. Cannot borrow self-sent messages as mutable, as it is behind an ampersand reference. The self is an ampersand reference, so the data it refers to cannot be borrowed. Okay. Okay, so what's the solution? We can't modify mock messenger to keep track of the messages because send method takes an immutable reference to self. Send message immutable reference to self. We also can take the suggestion from the error to use @mut self in both MPL method and trait definition, as suggested here. Self is an ampersand reference, so the data it refers to another bar. Consider changing this to be mutable reference in the IMPL and the trait definition. Yeah. Mutable, that was the suggestion. Okay, but we don't want to change the messenger trait solely for the sake of testing. Instead, we need to find a way to make our test code work correctly with our existing design. This is a situation in which interior mutability can help. We store the send messages within refcell t, and then send method will be able to modify send messages to store messages we've seen. Where's the refcell? Refcell is here. Refcell. Send message. That's the difference. Refcell ref cell new. It's just ref cell because it's a struct. New, so it will create a new vector. And then here in send, message. Okay, message is now slice string. Oh, it has been slice string. Borrow mut. Do we have it there? This is send. Messenger for mock messenger. And this one is just sent message push. Okay, that's the difference. Here, borrow mut. And then you push borrow mutable, maybe. Because this is ref cell now. Okay, so maybe ref cell has this function. Push string from message. Okay. Function, it sends an over 25% warning message. Okay. The sent message field is now of type, okay, we've seen that, ref cell, instead of vex string. In the new function, we create a new ref cell vex string instance around the empty vector. For the implementation of the send method, the first parameter is still an immutable borrow self, which matches the trait definition. We call borrow mut on the ref cell. Okay, so it was for the ref cell. In self-sent messages to get a mutable reference to the value inside ref cell. Borrow mut to get a mutable reference. Ah, okay. So that's why it's named as borrow mut. Because you want to borrow, but a mutable reference. You want to borrow from a mutable reference. No, how should we interpret this? You wanted to get a mutable reference to the value, mutable reference to the value inside. So a vec string is a mutable reference to the vector to keep track of the messages sent during the test. Okay. The last change we have to make is in the assertion to see how many items in the inner vector call borrow on ref cell backstring to get an immutable reference to the vector. Now you have seen how to use ref cell. Let's dig into how it works. Okay. Let's dig into how it works. Okay. We'll have more clarity here. When creating immutable and mutable references, we use ampersand and ampersand. Yeah, this is mutable reference. Syntax respectively. With ref cell, we use the borrow and borrow mut. So borrow would be for this one. Borrow mut would be for this one, which are part of the safe API that belongs to ref cell. The borrow method returns the smart pointer type ref, and borrow mut returns the smart pointer type ref mut. Both types implement deref, so we can treat them like regular references. Ref cell keeps track of how many ref and ref mut smart pointers are currently active. Each time we call borrow, the ref cell increases its count on how many immutable borrows are active. When a ref value goes out of scope, the count of immutable borrows goes down by 1. Just like the compile time borrowing rules, ref cell lets us have many immutable borrows or one mutable borrow at any point in time. So many immutable borrows. Okay, you can do many immutable borrows or one mutable borrow at a given point in time. If we try to violate these rules rather than getting a compiler error as we would with references, implementation ref cell will panic at runtime. Listing 15-23 shows a modification of the implementation of send. In listing 15-22, we deliberately trying to create two mutable borrows active for the same scope to illustrate that ref cell prevents us from doing this at runtime. What's in here? Messenger for mock messengers and mutable one borrow. Two borrow. One borrow push, two borrow push. Why it will not compile? Okay, we create a variable one borrow or refmut. Smart pointer return from borrow mat. Then we create another immutable borrow in the same way in the variable to borrow. This makes two mutable references in the same scope. Okay, two mutable references in the same scope which isn't allowed. When we run the test for a library, the code in listing 15-23 will compile without any errors, but the test will fail. Let's see what is in here. Oops. Here. Running one test, it failed. Okay, it says it panicked. It panicked. Why? Already borrow mutable. Error. In which line? 60. We don't see the line number here. What is the explanation? Notice that the code panic with the message already borrowed not error. This is how ref cell handles violations of the borrowing rules at runtime. Sends over 25% warning message. Where is that? Okay. This is how handles violation of the borrowing rules at runtime. The code panic. Okay. The code panic. It's not compile time. Okay. It's at runtime, so the code will panic. Choosing to catch borrowing errors at runtime rather than compile time, as we've done here, means you potentially be finding mistakes in your code later in the development process, possibly not until your code was deployed to production. Choosing to catch borrowing errors. Yeah. So error handling. However, using ref cell makes it possible to write a mock object that can modify itself to keep track of the messages it has seen while you're using in context where only immutable values are allowed. You can use ref cell despite its trade-offs to get more functionality than regular references provide. Allowing multiple owners of mutable data with RC reference counter and ref cell. Interior mutability. Yeah. Is it interior or internal? Interior. Okay. A common way to use ref cell is in combination with RC reference counter. Recall that reference counter lets you have multiple owners of some data, but it only gives immutable access. This one gives immutable access. If you have an RCT that holds a ref cell, you can get a value that can have multiple owners and then you can mutate. Oh. For example, recall the cons list in example 15-18 where we use RC to allow multiple lists to share ownership of another list. Because RC holds only immutable values, we can change any of the values in the list once we've created them. Yeah, RC holds only immutable, so we cannot change it. Let's add in ref cell for its ability to change the values in the list. In the cons definition, we can modify the values stored in all the lists. Okay, let's take a look. Cons. So ref cell can modify the values stored in all the list. This is RC. Okay, RC can only hold immutable values. Yeah, so here, so the list is immutable also. Okay, then here, RC new, ref cell new. RC new, ref cell new. We create a value that is an instance of RC ref cell and store it in a variable named value. So we can access it directly later. Then we create a list in A with a cons. Okay, A, this is like the one in the code. Let's see, new cons. Okay, RC clone, correct new. Okay, so there's an RC clone here at value. So we're cloning the value. That's the explanation. You need to clone value, so both A and value have ownership of the inner 5 value rather than transferring ownership from value to A or having A borrow from value. A list in A. Create a list in A with cons variant that holds value here. We need to clone value, clone value, so both A and value have ownership of the inner 5, so they are pointing to the same. Okay, rather than transferring ownership from value, to A, or having a borrow from value, we wrap the list A in rect C, no, not rect C, but reference counter RC, so that when we create lists B and C, they can both refer to A. How can I refer to A? A ref cell new. Here, RC clone. Okay. Where are we? After we created the list in A, B, and C, we want to attend to the value in value. We do this by calling borrowMut on value, which uses the automatic dereferencing feature we discussed here. Okay. Chapter 5, to dereference RC to the inner ref cell value, the borrowMut methods returns refMut pointer. And we use the dereference operator on it and change the inner value. So I don't think I understood everything there. Maybe let's take another time to really understand this part. So do that in the following day, in another day, so that we know what is mentioned here in the book. I think before we can move on to this one, let's come back to interior mutability pattern and really understand what are the advantages here. So let's save that for another day. So I have to end here for now. Hope to see you on the next day. But first, let me thank my supporters.